Hello everybody, welcome to Embetronics. We came up with a new tutorial series of bootloader design and implementation for STM32 devices. In this video, we will see the basics of bootloader and its design. What is a bootloader? A bootloader is a special operating system software that does some functions like hardware initialization and loads the actual application. This is also called as a boot program or bootstrap loader. When you power up the system, this is the first piece of code that runs. Some of the systems like small microcontroller doesn't have the bootloader, so the application will be running directly. We may have some questions like, why do we run an extra piece of code instead of running the application directly? You will get your answer at the end of this series. There are many things that we can do using the bootloader like firmware update. Nowadays, we are using many gadgets like a smartwatch, smartphone, Bluetooth earphones, and many more. What we are doing when any OS and firmware updates are available, we are downloading the firmware to our mobile phone and connect the mobile phone to the gadgets like a smartwatch. Then start flashing the firmware images. If we don't have the bootloader, how come the smartwatch knows where to write the new firmware image? If we use the bootloader, then that will take care of that. So we can load the application without the programmer or debugger. The next use case is security. If you are making some secure products, then the bootloader can check the application CRC every time during the boot. If someone has changed the application or it has any memory corruption, the CRC verification will fail and we can take the necessary action. Like this, many other use cases are also there. Okay, we have a basic understanding of bootloader. Now, we have to know the booting process of the microcontroller. What happens when you press the reset button or power up the ARM Cortex M4? When you press the reset button or microcontroller powers up, the PC is loaded with the value of 0. Memory 0 will have the stack's starting address. In my case, stack address is 0x200000. So the stack address will be copied to the MSB register. Now the MSB register has the stack's starting address. Then the program counter increments by 4. Zero x 4 has the address of the reset handler. So it jumps to the reset handler. In the reset handler, it will initialize the hardware, then copy the initialized data, which means initialized global variable and static variable to RAM. Then copy the uninitialized data to RAM and initialize it with 0. Finally, it calls our main function. This is what happens when we power up the controller or press the reset button. What if our project has a bootloader? Then we will be having separate binaries for the bootloader and the application. Each binary has its own vector table. We have placed the bootloader at 0 and application into some other location. When the microcontroller powers up, it will run the bootloader first as it sits in the 0x0 location. As we discussed earlier, it takes the stack address from the 0x0 and stores that to the MSB register. Then it reads the reset handler's address and goes to the reset handler of the bootloader. It does some operations. Once it has finished its job, it will call the main function. After that, it calls the applications vector table, and we have to update the MSP with the applications stack address. Then it takes the application's reset handler address and calls the reset handler. In the reset handler, it does the same operation that we explained previously and calls the main function. Let's recap it. When you press the reset button, it starts from the 0x0 address and updates the MSP register. Then it goes to the bootloader's reset handler, bootloader's main, application's reset handler, and application's main function. Does it make sense? Okay. Is there any bootloader available already in the microcontroller? Yes, there is. Each latest microcontroller has a system bootloader that is provided by the chip manufacturer. It will be stored in the ROM section. The microcontroller has boot pins. Using that, we can run this system bootloader. Why do we need a custom bootloader when we have a system bootloader? Using this system bootloader, we cannot do whatever we wish to. If we want to implement advanced stuff like OTA with our own algorithm, then it is good to have our own bootloader. If you think you can achieve your goal using the system bootloader, then you don't need to write a new bootloader. But in my case, I want to implement more features in the firmware update process, so I want the custom one. I hope you may have some overview of how the bootloader works and how the application has been called. Now let's move specifically to the STM32 device. STM32 F767GI memory. The code memory starts from the 0 to 1FFFFFF. The code memory has been divided into ITCM RAM, reserved, system memory, reserved, flash memory on ITCM, reserved, flash memory on AXIM interface, and many more sections. Let's see the flash memory. It has a 2 MB flash. We can use this 2 MB flash as a single bank or two banks based on the ND bank's value. We are going to utilize this complete 2 MB flash in a single bank mode. Flash is starting from 0x08000000. You may have a doubt. I said earlier that microcontroller starts from the 0x0, but our code will be present over there somewhere in 0x08000000. How is it possible? It is possible with the help of boot configuration and memory alias. Normally, most of the microcontrollers will have one or few boot pins. In my STM32F7, only one pin is available. Based on this GPIO state, the controller will decide where to start. If the boot pin is 0, then it starts from the 0x00200000. Otherwise, it starts from the 0x00100000. But if you check the STM32F4, it is different. It has two boot pins. Based on the two GPIOs, it will start from the flash memory or system memory or SRAM memory. In my case, my GPIO will be 0. So it will start from 0x00200000. Still have some doubts, right? Yes, this memory alias will clear your doubts. I told you that microcontroller will be starting from 0. When this boot pin is 0, then 0 will be an alias of 0x00200000. Otherwise, 0 is an alias of 0x00100000. So, this is what memory alias is. You are fine now, right? Okay. Now, I will explain to you that how I have partitioned the flash memory. I have a 2 MB of flash from 0x08000000 to 0x081FFFF. As I am using the flash memory as a single bank, then I have sector 0 to sector 11, totally 12 sectors. I will place my bootloader into sector 0 and sector 1, that is 64 KB. I am leaving the sector 2 and sector 3 as it is. For configurations, I have assigned sector 4 of 128 KB. I know that I may not need the 128 KB for this, but let it be for now. The actual application which will run is placed into sector 5 and sector 6, which is 512 KB, and also I have planned to keep the current version of the application and the previous version of the application as a backup. For that purpose, I have allocated 2 slots. These 2 slots size is also 512 KB. When you want to update the firmware or application, then we have to write the new firmware or application into these slots. Okay, we have allocated enough memories for enough things. I may update this memory structure later if I want to add any features. So check out my website given below for the latest details. We have everything ready, haven't we? Oops, we have forgotten to design the bootloader and application. Let's design that. First, we will see a bootloader operation and later we see the application. When you press the reset button, the bootloader starts running from the 0x08000000. One more thing I want to clarify. We are placing our bootloader code into 0x08000000 and the controller starts from 0x00200000 because in the boot mode I told you that if the boot pin is 0, then it will start from the 0x00200000. Actually, both are pointing to the same memory. Only the difference is the bus that is used to access that memory. In STM32F767GI, 0x00200000 will be accessed by using the ITCM bus, where we have permission only to read and execute and not write. But the address 0x08000000 will be accessed by the AXI bus, where we have read, write and execute permission. That's why we are writing our bootloader to that memory and the processor will read that memory using the ITCM bus. For understanding, you can assume that 0x00200000 is the alias of 0x08000000. If you want to verify this, then write the bootloader into 0x08000000 and read the 0x00200000. The same data will be present in both addresses. Let's continue to the bootloader. When the bootloader starts, it fetches the stack pointer value and stores it to the MSP. Then it jumps to the reset handler of the bootloader followed by the main function. We have to define one GPIO as an input. If the GPIO is low, then assume that the user wants to update the firmware. So we have to receive the data from the UART and write the received data to slot 1 or 2. Then we reset the controller. So again bootloader starts and checks the GPIO state. Now as the firmware has been updated, the GPIO will be high. So it will go here. I told you that I have allotted 128 KB for configurations. There I will write the reboot cause whenever I reset in a special condition. For example, the very first time it will have some default value. That means it is the first time boot. It copies the application from slot 1 and verifies the CRC. If the CRC verification is successful, then it starts the application. If has been failed, that means some memory got corrupted or someone has changed the application, right? So in that case, we will stop and don't run the application. If it is a normal boot and not the first time, it will check the actual application CRC, and if that is fine, then run the application. Otherwise, it will not run the application. If the reboot cause is OTA request, that means the application has requested the OTA firmware or application update. In that case, the bootloader will receive the data from the UART and stores it in one of the slots. There are some situations when the user wants to go back to the previous version of the application, like when the user is facing some problem with the current latest application and he wants to downgrade. In that time, it copies the application from the slot 1 or slot 2 who has the old version and does the same process. We may add some features or corrections to this logic while implementing the bootloader. So I request you to check the website for the latest content. The website link has been given in the description. Now we will move to the application. Once the bootloader starts, it will check the GPIO, and if that is high, then reads the reboot cause and assume that this is a normal boot. It will verify the CRC, and if the CRC check passes, then it runs the application. So it will come here. Here we are assigning one GPIO interrupt that helps the application to know whether the user wants to update the application. If the interrupt got triggered, then the user wants to update the newer application. If the interrupt is not triggered, then it will blink the LED and check this again and again in a loop. This is a very simple application you can implement based on your need. When the interrupt has arrived, it will write the reboot reason as an OTA request and resets the controller. Now, what will happen? The bootloader starts and checks the boot button. It is not pressed, then reads the reboot cause. The application has been written the reboot cause as an OTA request. So it will go here and receives the data from the UART and writes to the slot. Then update the reboot cause as a normal boot and it resets. Now the microcontroller bootloader will start and read the reboot cause as a normal boot, then verify the CRC and runs the latest application. In our upcoming tutorial videos, we will break this into multiple tasks and implement them one by one. In the final video, we will be having these complete logics are implemented. Please check the description where I have provided the all required links. Don't worry, I will never force you to subscribe our YouTube channel. I hate that. If you like our content, then you will automatically subscribe to us. Thank you all. See you again in the next video.